Hello and welcome back to the second lecture of the first part of AI in medicine. In this lecture, we're going to talk about the different types of machine learning. As discussed in our first lecture, computational power has grown to the point of instant calculations and the ability to evaluate new data according to previously assessed data in real time. Now, AI can potentially look at millions of scans in a short period of time with accuracy. And it is the combination of these two that is contributing to artificial intelligence machine learning becoming a disruptive technology. So once again, machine learning is the ability of a computer to learn from experience, to modify its processing on the basis of newly acquired information. This process can be based on a simple decision-making tree, such as an if-when loop, which leads to a conclusion, or using deep learning algorithms which imitate the human brain in processing several types of data and creating patterns for use in decision-making through neural networks, which we've already talked about quite a bit so far. Now, once again, there are basically three types of algorithms: unsupervised learning, supervised learning, and reinforcement learning. Let's talk a little bit more about these algorithms. Now, unsupervised learning algorithms are used to generally uncover naturally occurring patterns or groupings in your data. And this is without targeting a specific outcome. Now, a use case for unsupervised learning in healthcare, for instance, is precision medicine, in which the goal is to uncover subsets of patients who share similar clinical or molecular characteristics and are, in theory, more likely to respond to targeting therapies directed at their shared underlying pathobiology. So this is an interesting application of machine learning, and probably one that will be leveraged more and more as we move forward in AI in medicine. Okay, so how about a graphical representation of unsupervised learning? So essentially it's clustering. So we start with a heterogeneous population of entities. So let's say in this case patients, and we perform unsupervised learning in the hope to find groupings or clusters of patients that share common characteristics. For example, in this case, it resulted in 3 clusters. For example, an unsupervised learning algorithm could be used to uncover subgroups of patients with sepsis who have distinct molecular and clinical characteristics and will respond differently to specific drugs, such as corticosteroids, which is, in a way, a little bit of a controversial treatment for sepsis, where there are some studies that indicate that the use of corticosteroids will reduce the risk of death, and other studies that show the opposite. And often when you have this kind of teetering between should we treat, should we not treat with a specific drug, let's say, it's often because the population is heterogeneous and some people will respond well to the treatment and it will reduce the risk of death, whereas other patients will do the opposite. They will not respond well to corticosteroids and it could actually be a little harmful. And this is where, if we could identify those subgroups, then that would lead us towards what was called personal medicine, but is now called precision medicine. Now, what if you have a large data set containing patients, once again, with their clinical features and their outcomes? And the outcome is simple, it's binary. Did they survive or did they not survive? Now, what you would like to do, of course, is learn from that data set, and then the next patient that comes in, you would be able to predict their outcome. Well, in this case, you have labeled patients. So you have an outcome, and it's your label essentially, for your data set. So in this case, we would be referring to supervised learning. Supervised learning is used to uncover the relationship between variables of interest and one or more target outcomes. For supervised problems, the target outcomes must be known. And that typically is one of the more costly aspects of doing research using supervised learning, is this need to have properly, correctly labeled data, which is also known as the ground truth. Now, for example, if researchers want to know whether a set of clinical features, as we saw in the previous slide, vital signs, laboratory tests, can predict ICU mortality, they could apply a supervised learning algorithm to a data set in which each patient record contains the set of clinical features of interest and a label specifying their outcome. All right, what types of supervised learning are there? Well, let's start by looking at our outcome. If our outcome is a categorical variable, then we would be interested in classification, as you are going to want to classify your entity, so let's say patients, into different groups or different bins or different levels of your categorical variable. If you are trying to predict a continuous measure, a continuous variable, then you would be performing regression. Now, regression is the process of predicting a continuous output. Great. You have linear regression. Most people have done some form of linear regression in their research through statistics. And your linear regression will basically be fitting a line of best fit, or your regression line, to two dimensions. Your independent variable, which is your x-axis, and your dependent variable, which is your y-axis. You're trying to predict y. What if it is not a linear fit? Then you are going to move towards what's called a polynomial regression, which can take on various different shapes. In this case, for instance, it's a polynomial ridge regression, which is more common if you're going to have a multi-dimensional problem, right? Now, what if we do have a categorical outcome, then it's classification, and it's the process of grouping data into qualitative bins. The first algorithm that comes to mind is decision trees. Here's a wonderful little figure of how decision trees work. You can also do what is called k nearest neighbor. In this case, it is a non-parametric approach to binning your data, essentially. And then finally, as we've already mentioned in the previous lecture, neural networks can also be used for classification, and this is where we get into the fun of developing AI/ML solutions for medical imaging problems, because your neural networks, when applied to images using what's called convolutional neural networks, provides you a way of classifying your images. So computer vision is the processing of an image to enable identification of image input and to provide an appropriate output. And so, just as I said before, one of the processes of being able to identify patterns in the input of an image to provide the output, which would be classification, is something that is becoming very, very important in the world of AI and medical imaging. So let's take a closer look at this convolutional neural network, or CNN. It is a form of deep learning. It was inspired by animal visual cortex, which is our own, for instance. Each neuron responds to stimulus in a small field, what's called a receptive field, and many neurons' receptive field overlap to form the whole visual field. So that's how we see. Now, this form of machine learning is mostly used for image and video recognition, as well as natural language processing. So what are the basic components of the CNN? Well, the first thing you have to start with is your input and the feature extraction from your image. And with this, we can detect features in the input. And for example, our input is a triangle shape of cheesecake with berries on top. Your next layers are going to be convolution layers, followed by pooling layers, and then fully connected layers. This is just overall. Now, at the end, you're going to want to have classification. So your model will be able to classify, in this case, for instance, let's just make it easy, a binary output of the probability of it being cheesecake. And in this case, we can assign the probability of 80% that this image represents cheesecake. So why CNNs? Well, first and foremost, CNNs learn features on their own. In many classical machine learning algorithms, features are engineered by us. And this is not always the best solution. They may not always be appropriate for the model. The different layers allow for more precise feature extraction. And there can be many layers and there can be many features. And so this gives the algorithm flexibility in order to select the best solution. So pretty much thanks to CNNs, the application of machine learning to medical imaging has just boomed in the past few years. Another reason is that medical images are one of the fastest growing data sources in healthcare. So we're getting more and more data, and not only that, but we're getting more and more quality data that's labeled, which gives us the opportunity to apply this wonderful machine learning algorithm, CNN, to this data. Also, the imaging data continues to become more complex, which, ironically is great for, machine learning and artificial intelligence, because the more complex the problem, the better suited AI ML is as a methodology. Now, machine learning can find relevant patterns within the data, reduce the mass amounts of data into important clinical contexts, which is also important for more ClinEpi work, bypass deficits of traditional methods using an automated approach. So you're in a sense, you have the ability to reduce bias. Now, of course, there are always a few limitations. One of them here, which is interesting, is called catastrophic forgetting. Machine learning and AI can learn a new task, certainly, and it's an iterative process, but it also overwrites the previous one. So that can be a limitation in your methodology. Cognition, the ability to build knowledge from interacting with the world through sensory and motor experiences and creating an abstract thought from there. We're not quite there yet with artificial intelligence. And imagination. So imagination and innovation relies on models we've already built about our world and extrapolating new scenarios from them. So right now, once again, artificial intelligence isn't there, but you can imagine people are working very hard at overcoming these three limitations as we speak. Okay, let me take a moment to go back to deep learning because it's so important. It is part of machine learning, of course, as we've discussed. And what I wanted to show you here was a little, visual of what I mean by deep learning and multiple layers. So you have on your left a simple neural network, as I said, input layer, middle or hidden layer, and then your output layer. On the right is the deep learning neural network, where your hidden layer has now become 4 hidden layers, and you can have many more than that in a very deep learning neural network. So, the deep learning is a subset of the machine learning, which is structured similar to the human brain processing, which once again we discussed in the first lecture. Now, taking into account multiple data sets at the same time, which are evaluated and processed for second and third different evaluations. So this is where it gets complex and where this complexity can lead to better accuracy for your problem. Now, every evaluation is carried out in a different layer. And so the layers of computation are called hidden layers. Inputs and outputs are invisible. So meaning that you're not in control of it, you don't work with it, you don't change it, they are part of the algorithm. Now each filter, in the case of CNNs, creates a different output. And so for simplicity, one can say that deep learning is a process in which an algorithm receives data. So let's just say Excel charts, so meaning the data in charts, images, etc., and then examines the data according to a predetermined pathway, which is your artificial neural network, that was developed specifically to solve the desired problem. The artificial neural network is developed according to a training set of data and is provided to train the algorithm to answer a specific question. The training data set must represent the problem it is being asked to solve to ensure accurate results. And this is the beginning of what I'm going to call oversight for when you do machine learning and to produce artificial intelligence solutions in medical research. There must be oversight. Just like any research, there's a requirement for you to make sure that your methodology is sound and that you can infer from your results to the greater population. Okay, so here is just a slide to give us a little perspective. This is the hype cycle for emerging technologies. It's already outdated. I'm sorry. It's 2 years old, 2018 from Gartner. And what it's showing you is the x-axis is time and the y-axis is expectations. Okay, and what you're looking for is in this curve, right, is in sections here. You have the innovation trigger, so the start, the peak of inflated expectations. So you're thinking, oh my God, this is going to be amazing. It's going to solve all our problems. And then the trough of disillusionment, which means like, oh God, it's not that great. And then you have the slope of enlightenment, which means that, oh, we're starting to figure out how to use this and make good use of it. And then the plateau of productivity is now we're using it. So if you look at these data points as some examples, you have, I remember smart dust was one of them. Flying autonomous vehicles is really right at the beginning of your innovation trigger here. Human augmentation, which has been going to 4D printing, knowledge graphs. So all these are just like, whoa, like crazy cool stuff. Quantum computing is always there, right? Oh, it's getting closer. As you can see, it's getting closer to the I guess I don't know reality, but I guess to the peak in this graph, which means inflated expectations, means it is really close to a reality, becoming a reality, and so people believe, right? But if you look here, right at the top in 2018 was the deep neural nets, the deep learning. So according to Gartner, deep learning is way up here, and I kind of believe it, right? What's going to happen is you're going to get this trough of disillusionment where the expectations of deep learning are just going to plummet because we're going to realize there's only so much we can do. Do I see it crashing this hard? Maybe not, because AI and deep learning truly are making some amazing tools, skills, development that is very helpful, and therefore the expectation will be softened a little bit in terms of the drop in expectation, because there are some very good products that are coming out of this technology. But I just thought I'd bring this up to you to show you that be a little cautious, believe in it, but just maybe not jump in completely yet. Just wait a little bit and slowly bring this into your research program or into your studies or into your interest. Just track it, bring it in, learn about it, but don't necessarily completely convert your research program into deep learning. Maybe just do it progressively. So I'm always talking about the 3 types of machine learning, which is supervised learning, unsupervised learning, And there's always this third, reinforcement learning, which, often gets left, to the side just because it's not used as much in our world. Let me explain. So reinforcement learning, in reinforcement learning, a model designer normally formulates the learning components, right? So that means the objective, the state, the action, the reward, what's going on, right? And he or she specifies the presentation and efficiency techniques, and then simply lets the reinforcement learning algorithm run until a solution, a good solution, is obtained. So for example, reinforcement learning has achieved, solving complex sequential decision-making problems in various healthcare domains, such as treatment in HIV, cancer, diabetes, schizophrenia, and sepsis. But the key here is sequential decision-making problems. There has to be kind of a path, right? And so, a good example to help you understand reinforcement learning is gaming. Okay, so even if you're not a gamer yourself, you can imagine all these, kids or young adults, or actually, I guess, from all generations, are sitting down and playing these, first-person shooter, what they call shooter games, where they run through a maze, shooting and teamwork and discovering. But how does the computer deal with all that input of information that's going on in the screen, plus the shooting and switching guns and all that kind of stuff? Well, reinforcement learning is a big component of that. It's essentially adapting the path to or for the avatar that's in the game. And so that's how it is done, is through this reinforcement learning, because when you have all the learning components there and the presentation, you need an algorithm that's just going to give you a solution. So if your avatar does this in this condition at this time, then react for a satisfactory solution, which means making the game fun and making the game challenging and abiding to the states and the parameters that you've set in your software. Anyway, applying that to healthcare, definitely on the way, definitely coming, definitely useful. But once again, if you're going to think reinforcement learning, think sequential decision-making problems. All right, this brings us to the end of lecture 2. Congratulations, that's 2 lectures down already. Next up in the third lecture, and actually the third and last for part 1, we're going to talk about AI and big data. See you there.